Good morning, everybody. A few quick words about my co-authors. Patty Gallego and Dorothy DeBlau are teachers. Patty was at Tri-Valley School in Healy. She moved on to Anchorage. Dorothy is still there. Without them, I wouldn't have anything to tell you today. They're a very important part of this project. Kim Morris is a research professional at the Geophysical Institute. And Delina Norris-Tull is a professor of education now at the University of Montana Western, but she was at UAF for many years. And she has been my education mentor, particularly as it relates to K-12. And that's a very important aspect. I needed mentoring, as it were, in K-12 education. I'm a full-time researcher, I'm a research professor. That means that my job contract with UAF doesn't require me to teach. So I don't really know a lot about education and how to talk to people and help them learn and understand. But in recent years, I've been working on integrating education into my research programs. And the overall goal of what I'm doing is to try and provide opportunities for teachers and students to learn science by doing science in their own backyard, place-based experiential learning. This has been partly driven by National Science Foundation requirements that as researchers, we must have broader impacts to our research. We must go beyond business as usual of teaching undergraduates, supervising graduate students, having a website maybe and things. What I'm going to talk about today, the Horseshoe Lake project here at Denali, the specific objectives were integrating the investigation of lake ice and snow cover into local ecosystem studies by mixed 3rd, 4th, and 5th grade classes at Tri-Valley School in Healy. And in so doing, contribute to some improved knowledge and perhaps even understanding of the ecosystem of Denali National Park and Preserve. This is not Horseshoe Lake. These are students at Nome, the charter school in Nome. They're drilling a hole in the ice. Now notice the ice is very bare. There's not a lot of snow on it. And notice these, I don't have Parkinson's. Notice these fracture lines here. The ice is heavily fractured, and the reason it's heavily fractured is it's got no snow on it. So it's subject to intense temperature variation and change. The ice contorts and deforms, not visible to the naked eye, but nevertheless it deforms and it becomes heavily fractured. These photographs, these are vertical air photographs taken from a height of about 6 feet. And my foot would fit within that frame. So is snow really such a good insulator? These are data taken at Horseshoe Lake in December 2003. Now, there's a study site set up on the lake. It's a 100-meter long transect marked every 5 meters by wooden stakes. And at every wooden stake, the snow depth is measured. So here you see the snow depth on a single day along that transect. And so you see the snow depth here. And the average snow depth was 0.16 meters, 16 centimeters. And in addition to measuring the snow depth, the temperature at the bottom of the snow on the ice cover was measured. And that's these data here. So you see that the temperatures were varied between 0 Celsius and -5 degrees Celsius, and the average temperature at the bottom was -3.6 degrees Celsius, while at the top of the snow, where the students were making the measurements, it was -21 degrees Celsius. So just 16 centimeters of snow, just that much, makes an enormous difference to the temperature at the top of the ice and throughout the remainder of the ice cover. So snow is a very effective insulator, although I would qualify that and say it's actually really the air that's trapped amongst the snow crystals that's providing the insulation, but the snow provides the matrix for the air that insulates. It's just like triple pane windows. And you can see how well related snow depth and bottom temperature are. In this graph here, we have a pretty strong linear relationship that the temperature on the bottom is strongly dependent on the snow depth. Where is Horseshoe Lake? It's about 2 kilometers from here. At lunchtime, you could walk down, get back in good time for this afternoon's session. We're right here at the moment. The visitor center, Horseshoe Lake, is right there, about 2 kilometers north. This is what it looked like on Sunday. This is how I prefer to see it, with all the water frozen. I'm kind of funny like that, but I like ice. These are 3rd, 4th, and 5th grade students who are making these measurements, going out on a regular basis during the winter with the teachers, with parents, with people from the Park Service and ANHAR to help. They measure the snow depth. They measure the temperature on the ice surface at the bottom of the snow. This is some students here doing that. They have these probes that we provide with a digital reader on top. They also measure the temperature at the top of the snow surface temperature. And they measure the ice thickness and take snow samples, as you see here, so they can go back to the classroom, weigh the snow samples, and calculate the density of the snow. And from the snow measurements, they get to heat flows. And I'll explain what that is. So they're measuring snow depth, they're measuring temperature at the top and the bottom of the snow, and they're taking snow samples from which they will calculate the snow density. And they also measure ice thickness. And here is a student measuring ice thickness. They measure ice thickness using basically an electrical circuit that's frozen into the ice. And the key part of the electrical circuit is a bare resistance wire. And when you attach a 12-volt battery to that, a resistance wire, as we all know, is going to warm up. And the wire is of known length. It has a toggle on the bottom, so you can't pull it out of the ice when you raise it up. But you raise it up as far as it will go, so the metal toggle comes up against the bottom of the ice. Then you measure the length of wire between the wooden handle you see in the student's hand and the ice surface. Subtract that from the total length, and you get the ice thickness. It's a really elegant way of making accurate measurements of ice thickness without disturbing the ice cover. It's also a neat illustration of Joule's law in action. James Prescott Joule, who's my scientific hero, because he comes from my hometown, Manchester, England. If you have snow depth and you have snow temperature at the top and the bottom, you can calculate the temperature gradient. That's the difference in temperature across a unit length of the snow cover, typically expressed in degrees Celsius per meter. If you have snow density, you can use empirically derived equations to convert snow density to thermal conductivity. Thermal conductivity is simply a measure of how well a material conducts heat. Or it's another way of expressing how poorly or how well a material insulates. That's what insulation's about, minimizing or maximizing heat flow, depending on how you want to look at it. Then if you have temperature gradient and thermal conductivity, you can calculate the conductive heat flow. And without conductive heat flow, there cannot be ice. As long as we conduct heat out of the ice and through the snow up to the atmosphere, the ice will grow. So the conductive heat flow, which is driven by the temperatures and the snow characteristics, determines our ice growth rate at the bottom, and thus the ice thickness. So quickly to conductive heat flow, you can see the values here around -7 to -10, and you'll notice that the fluctuations in heat flow are relating to the snow bottom temperature measurements and the snow depth measurements. The conductive heat flow has to be strongly correlated with the snow characteristics. The students have been doing this for 3 years now. This is their entire record. Along the bottom we've got winter from November through to April, and each symbol represents a day that they went out, made measurements, and each of these symbols is an average of those 21 measurements or derived data points that they obtain. So here we have ice thickness, we have snow depth on top of the ice, snow density, temperature at the surface of the snow, air temperature in effect, and our heat flow. I'm not going to go into great detail on what all these data mean. That's not so important in this context. The important point is that young school children have gone out and made these incredible measurements. They're not alone. The students who are going down to Horseshoe Lake are participants in Allison, the Alaska Lake Ice and Snow Observatory Network. The network comprises teachers and students in schools all around the state, from Barrow in the north, out to Wales in the west on the Bering Strait, down to the Kenai and Anchorage Bowl area. Quite a number of bush sites, Shagaluk, Huslia, Hughes, Mentasta, and so on. All the students are going out using the same equipment that we use in our own studies at Poker Flat, Chattanooga, just north of Fairbanks. And they're giving us a much broader perspective on the variation of lake ice thickness, snow depth, density, conductive heat flow around the state, because as you all know, we don't have a single uniform winter climate. It varies greatly around the state, and that affects how thick the ice grows, because the air temperatures differ, the amount of snow that accumulates, the density of the snow that accumulates varies all around the state. So these school children in Healy and around the state are contributing to a much improved knowledge and understanding of lake ice variability around the state. And that's very important because freshwater ice is a very sensitive indicator of climate variation and change. And in a time of great change in the cryosphere in Alaska alone, it's kind of useful to have baseline data of these kind. So to conclude, as far as we're aware, the Tri-Valley school kids who've been going down to Horseshoe Lake on a regular basis for 3 winters now, they're about to begin a 4th winter. Let's face it, be realistic, winter's coming. I look upon that's a great thing, because I love ice and snow. But as far as we're aware, they're the first people to make measurements of ice and snow down at Horseshoe Lake, so they're creating new knowledge. They're citizen scientists, and they're contributing to the knowledge and understanding of the ecosystem of this great park. They're learning science by being scientists, by being partners in science with me and Kim as part of Allison. And finally, I would say, and this is a very important point, young school kids can be good scientists. And I'll leave it at that and just say thank you to all the people who've made this possible. I haven't done it on my own. And I'll let you read that, and if there are any questions, I'd be glad to answer them.